In this hopefully short video, I'll be discussing the concept of impulse. The top here offers you a bit of a definition of impulse. Just to summarize, it says that there is a change in momentum which is caused by an unbalanced force which is applied to an object over a period of time. And you can see that all in the equation that comes after it. Impulse equals unbalanced force times time, which is the same as change in momentum. And so when we're going through this, we'll be talking about things in that regard. So the first one here, problem number 1 should be pretty basic. It's saying just find the change in momentums for these different objects. All right, we've got the unbalanced force, we've got the time, we're trying to calculate change in momentum. You have to remember that change in momentum then equals unbalanced force times time. All right, and we're just given both of those things. So for A, change in momentum is 30 times 0.5, which is 15 kilogram meters per second. All right, for B, the change in momentum equals unbalanced force times time, which is 12 times 25. So in this one, it's 300 kilogram meters per second. And then for C, unbalanced force, again, just take them, multiply them by each other, 0.2 times 15. And when you do that, you get the change in momentum equals 3 kilogram meters per second. So that one is not terribly hard. For problem number 2, we have to do a little bit more here. It says find the change in velocity given these FUs, T's, and masses. And so to think about this one, we know the change in momentum equals FU times T. We also know that change in momentum equals mass times change in velocity. All right, because typically speaking, the mass of an object will stay constant. And so if it's change in velocity, then you can multiply it by the mass, you get change in momentum. And we can combine those two together and solve for change in velocity. And what we get is change in velocity equals FUT over m. All right, so if you just find the change in momentum and then divide it by the mass, you should be good to go. And so for A then, change in velocity is going to be 20 times 0.8 divided by its mass, which is 2. On the top there we get 16 divided by 2, which is 8 meters per second. On the second one, similar problem, we're going to set it up exactly the same way. Change in velocity here equals 60 times 0.25 over 500 grams, which is 0.5 kilograms. It's got to be in kilograms, so 0.5. All right. So when we do that, 60 times 0.25 is equal to 15. 15 divided by 0.5 is 30 meters per second. And then I've given you a couple problems here that also relate to momentum. And so this first one has to do with a bullet that's firing from a gun. I said that it receives a force of 100 newtons over a period of 0.3 seconds as it accelerates through the barrel. And so what we'll do on one of these impulse problems is a lot of times I'll give you what you need to find out the initial momentum of an object. And so in this case, we're talking about the bullet. And so what we can do is we can find delta P for the bullet while it's in the gun. We're going to presume that it started off at 0 meters per second for that bullet. And so we know change in momentum equals FUT, which in this case equals 100 times 0.003. Okay, and then if you do that, you find that the change in momentum equals 0.3 kilogram meters per second. All right, then we go to this initial situation. It's a little bit confusing because this initial situation is still after the gun fired. What we're doing is after the gun fired, but before it hits the can. So the only thing moving after the gun fires is going to be the bullet. That's what we're going to be considering anyway. And we know that this bullet on our velocity versus mass graph here. We know the bullet has a mass of 2 grams, which is 0.002 kilograms. We know that it has a momentum of 0.3 kilogram meters per second, because that's what we got from that impulse equation. So that was what the momentum that the bullet is starting out with here. There's the can, which has a mass of 100 grams, which is 0.1 kilograms. All right, and it is not moving. You don't have to do it per se on this problem, but you can figure it out, and you can find that the velocity here is 150 meters per second. So then, in the second part of this problem, the can has been hit, and the can is moving. We know that the total momentum here is equal to 0.3 kilogram meters per second from the first part. So we know total momentum equals 0.3 kilogram meters per second. On this side, which means that total momentum equals 0.3 kilogram meters per second on this side. And it won't always be what you got from your impulse, but because the impulse was what went into the bullet, and the bullet is the only thing that's moving in the first case, then it ends up being our total momentum as well. We know here that the can is moving with a velocity of 2 meters per second in the end, and so what I'll do here is I'll make my little diagram for the can. It has a mass of 0.1 kilograms, and I've said that its velocity is 2 meters per second. And so what I know there then, if you go through and calculate its momentum, you just take 2 times 0.1 and you get 0.2 kilogram meters per second for its momentum. So the bullet has to have the rest. All right, it needs to be a total of 0.3. The can has 0.2. That means the remaining left in the bullet is 0.1. It still has a mass of 0.002 kilograms. And we know here that its momentum is 0.1 kilogram meters per second. And again, if you take its mass and you take its momentum and you divide it by its mass, you can get its velocity. And when we do that, we get 50 meters per second. Clearly, everything's not to scale here. It's hard to draw it so that everything's to scale, but as long as you get the general idea, hopefully that should be good to go. And so V final for this bullet is equal 50 meters per second. All right. For problem number 4, it's very similar. We've got a shopping cart. It's 100 kilograms. I say that it's put under a force of 40 newtons for 5 seconds. And so we know the change in momentum here equals Fu times t. Okay, in this case then, change in momentum equals 40 times 5, which equals 200 kilogram meters per second. So we've got a cart that's filled and a cart that is empty. The one that's filled is the one that was originally pushed. We're going to assume that both carts started out at rest, but now we've pushed this first one so that it has a momentum of 200 kilogram meters per second. It has a mass of 100 kilograms, and so I can do a little bit of thinking here, and I'll say we've got 100 kilograms for the mass. We know that the momentum here given to it by the force was 200 kilogram meters per second. All right, and then a little math there, dividing the momentum by the mass, we get that it is going 2 meters per second originally. Then we've got that other cart, which has a mass of 20 kilograms, and it is not moving at all. Then for the final situation here, first of all, we know that the total momentum has to be the same, all right, because of law of conservation of momentum. So we know that total momentum in this case equals 200 kilogram meters per second. So this other one on this side, P total, also has to equal 200 kilogram meters per second. I've said the carts have kind of combined and mangled together into one object here. And so if they are all one object, then the mass is 120 kilograms. Because of the law of conservation of momentum then, I know that the momentum here, the combined momentum of those is 200 kilogram meters per second. All right, and then if you divide that momentum by the mass, you end up getting a velocity here of 1.67 meters per second. So that should give you a pretty general idea of how these impulse problems work. I kind of don't like that you didn't see an example here where the total momentum was not equal to the impulse, but I will try and do some examples in class so that you can see that. Because we don't always have this weird thing that happens where you calculate the impulse and then it ends up equaling the same thing as the total momentum. So if you had an object hitting another object that was moving, for instance, that would be something different. Or we can do impulse after the collision instead of before the collision. And so I'll try and give you some examples in class of some different things, but hopefully this gives you a pretty good general idea of how impulse works.